Good afternoon, everyone. First, sorry for not being able to come to Atlanta in person due to visa issues. I'm Meng from Peking University. Today, I will share with you some of our recent work on verified neural planner for multi-robot systems. First, let's look at some motivating examples. As you can see on the left, a fleet of heterogeneous robots, including area and ground vehicles, can be deployed to remote areas to maintain a large field of EV panels. The routine tasks specified as linear topological formulas, including to scan transformers to monitor temperature and repel if needed, to detect obstructions on the panels so as to wash the surface or mow the grass. On the right, you can see a scenario of smart hospitals where different ground vehicles provide services to the hospital staff, including to guide patients to doctors, to deliver medicine, to monitor different rooms. Such tasks can also be specified as topological formulas, which, however, are generated online or according to daily needs. It can be seen from the simulations that multi-robot systems can be rather efficient by acting collaboratively and concurrently. On an even larger scale, consider a fleet of UGVs and UAVs that are deployed after earthquake for relief. There are numerous areas or sites that require different tasks, such as delivery of goods to different households, or to search and inspect injured person, or to assist numerous moving objects of interest. Again, these tasks are generated online and specified as logic formulas. Over the mission duration, in total 80 robots are deployed fulfilling 30 tasks and 500 subtasks. It can be seen that collaborations and coordinations are both essential on the mission level and on the local task level. How about a more challenging case? The multi-robot system of UAVs in green and UGVs in blue are tasked to capture the targets in red that are constantly moving and protect resources in yellow that are previously unknown. Notice that these tasks are all dynamic or unknown in the sense that they cannot be planned beforehand, and collaborative in the sense that one robot cannot accomplish any task alone. Similarly as before, it can be seen in the middle figure that the assignment of each task changes dynamically and frequently. These scenarios share four common aspects. To begin with, the overall complex task should be analyzed first and decomposed into subtasks that may have temporal and spatial constraints. Then, these tasks should be assigned to different subteams or robots to minimize a common objective function subject to these constraints. Moreover, as the scene is unknown and dynamic, meaning that new tasks could be generated and robots may fail, the new and old tasks should be planned together. Lastly, during the execution of each task, the assigned subteams should collaborate both on low-level control given their dynamic constraints and online updates of the environment. There are numerous notable challenges associated with the task and the motion planning problem for multi-robot systems. Namely, the planning complexity is often combinatorial with respect to the number of tasks and robots. The constraints among the subtasks are crucial for the correctness of the task involving both spatial and temporal constraints. The utility of a subtask collaborating on a common task, such as time and fuel cost, is often non-additive, marginal, and hard to estimate. The dynamic and uncertain environment requires adaptation both on the high-level task and on low-level motion. Our objective is to find the correct, complete, and adaptive approach to tackle some of these challenges. The proposed approach has the following architecture. Namely, it takes complex collaborative tasks specified as logical formulas, which are decomposed by partial ordering analyze and assigned by receding horizon B and B. Then, a local coordination and adaptation scheme is proposed for fast adaptation to dynamic tasks and motion constraints. Then, a learning module is trained offline and inferred online to predict initial solutions, search heuristics, and key parameters as to accelerate online planning. Finally, the local plans executed by collaboration and partial synchronization with updates on semantic labels and execution status. Linear temporal logic formulas are adopted to specify the desired temporal constraints among the instances of different tasks by propositional and temporal operators. For instance, the surveillance and sequential visits over different regions can be constructed by the eventually operator, and responses upon observations via the implies operator. For a fast and trackable decomposition, the task is first converted to a bookie automaton, which is then processed by removing redundant and infeasible edges, and then analyzed to generate a set of relaxed, partially ordered subtasks as the set of R posetsets. Then, the R posetsets contains different sets of subtasks and their partial ordering in terms of predecessence and concurrency. Given the relaxed poset of subtasks, they are assigned to the robots via branch and bound search algorithm. The efficiency of this algorithm can be greatly improved by branching under partial ordering, bounding the minimum make span given the estimated collaborative utility. Furthermore, as new tasks are triggered and released via online observation, the R posetsets are updated by computing the product of remaining subtasks and new R posetsets. Accordingly, the branch and band algorithm is performed in a receding horizon fashion, meaning that the subtasks to be assigned are updated online, which are essential for nearby new tasks. What if the features or task targets associated with the subtasks are constantly moving? In this case, constant replanning by the previous search algorithm would lead to high planning complexity and often oscillations in the local plans. Thus, a distributed correlation formation algorithm is proposed for the robots to change subteams or correlations for the set of subtasks. The key idea is that neighboring robots could negotiate potentially switch their assigned correlation. An assignment is stable if it cannot be improved under any key consecutive switches. This algorithm is distributed, complete, at any time, which has a key serial stability guarantee, especially when the hyperparameter key is chosen uniformly as 1, the KSS guarantee is equivalent to the Nash stable solution. While when k equals to the number of robots, KSS solution is the global optimal. Convergence speed and the solution quality of the previous algorithm depends heavily on two factors. First, the initial assignment and the choice of parameter k for each robot. Thus, to accelerate the planning process, a neural accelerator is proposed that is based on the heterogeneous graph attention neural net, which is the HGAN network. It takes as input the bipartite graph over the robots and the tasks with specific attributes of the nodes and edges, and predict the final KSS assignment and the key parameter. Given the original KSS algorithm, the neural accelerator can be trained in a supervised way, offline, by generating different planning instances and solutions. Once trained, the prediction can be used to generate high-quality initial solutions and good choices for the parameter k. The benefits of combining the two is best illustrated by this figure. Namely, the KSCO plus accelerator can kickstart with a good initial solution and converges faster to a high-quality solution as the black line. This solution is further improved by the KS-core algorithm, and the final convergence to a KSS solution is still guaranteed. This is in clear contrast to blindly follow the assignment recommended by the neural accelerator as the red line. Such combinations can also be applied to the planning of collaborative motion strategy, such as to predict the action sequences. Similar results are obtained as shown in the video in the case of a dynamic capture, which are omitted here due to limited time. To sum up, the proposed framework follows a hierarchical structure for automaton-based task decomposition, search-based task assignment, optimization-based task execution, and rolling-based task adaptation. Neural planners can be adopted as an accelerator for both the task planning and the motion planning for multi-robot systems. The learned heuristics and predictions are verified and improved by the model-based planning modules, which is particularly useful for fast online adaptation with performance guarantee in unknown and dynamic environments. Such a framework has been adopted in numerous multi-robot applications. For instance, the multi-operator and multi-robot fleets are deployed to explore unknown areas and fulfill online tasks, or to collaborate in complex scenes under communication constraints, or to explore and inspect different clusters of 3D structures, or to monitor dynamic targets under uncertainty constraints. More details can be found in my personal page. Thanks for your attention. That's all I have, and I will be happy to take questions. Yes.
Oh, hi. I'm glad you're here. I'm really sorry you couldn't make it. Any questions from the audience? So I have a question. I think I didn't quite follow where the learning came into play. So that you have a task in LTL, you decompose it, use the view key, you do really cool stuff there. Where's the interface between the learned model and the task description?
So the learning comes to play when we want to actually decide the assignment. So what we come across is that whenever you want to do assignment, you need to estimate the quality or the feasibility of a group of robots to accomplish this subtask. And this is often subject to very hard constraints and the dynamic environment. And to actually get a reasonable estimation of the quality or the feasibility, you need to solve a very big optimization problem. If you have a model-based method, of course we always do. We always design a model-based method and then solve it, and then return the results to the high-level planner and to make a reasonable decision. But the problem is that when you have to do this a lot of times online, in case there's so many moving components in the environment, then this becomes increasingly slow. So our idea is that you have a perfect model-based method, then you generate a lot of planning instances and then high-quality solutions. And then you use them to learn whatever you are interested in the model-based method, for instance, parameters, initial solutions, hyperparameters, whatever. And then you use this learned model online to actually kickstart the model-based method to get a good solution as early as possible, or even feedback a good estimate of the collaboration quality or the utility function to the high-level planner so that it can make a better assignment or task planning results in a reasonable amount of time. So I didn't have time to dig into the learning to actually accelerate not only the local collaboration and task level, but also the similar approach can be applied to the collaborative motion design, as shown in the collaborative, this dynamic capture, where each agent needs to decide where you want to go and which role you want to play to actually capture the target. And this is a very long-term optimization-based problem, and this is only a small part of a big assignment problem, right? You need to decide maybe another group of robots to do another kind of subtasks. So you need to estimate first how well they would perform in this subtask. And that's where we use the similar framework to estimate this kind of quality.
Okay, thank you so much. There's another question, but in the interest of time, I think we're going to move on. Contact them individually. Okay, sorry about that. Our next speaker is Cheng Liu from Carnegie Mellon University. And yeah, take it away, Cheng Liu.